So indeed, L1, L2. So let me start where I ended up last time, and let's try to be a little bit more specific. So let's talk about compressible fluid. So I can maybe write down just the equation, at least schematically. So what we're looking at is something like this. So you have d0 plus divergence of rho u equals 0. And you have something like this. So you have rho dtu plus rho u dot grad. And you have the level of pressure, and it's equal to maybe there is a parameter. And I do this case schematically. I have mu times Laplace. Okay, I just do this case schematically. So the idea is the following. So u is my velocity. Rho of t and x is just a positive function. It's just density. It's the density of. Okay, so the incompressible equation is just rho equal 1. Divergence of u is 0. And then pressure is given to you. This will be the incompressible Stokes. In the case of compressible fluid, if you let density free, then you need to give yourself a law of pressure. And typically, the so-called barotropic model is simply that you take pressure to be a power of density. Right? This is sort of the typical model. And I want to describe what dissipation is in this model. I just think that I can either ignore dissipation. So if there is no dissipation, if you want, it's referred to, this is Euler. And if you put some dissipation, this is Navier-Stokes, and there are various ways in which you can put it. Again, I just want to put it schematically. So mu is the viscosity in your problem. So either you have a non-viscous problem, mu equals 0, this is Euler, or you have a viscous problem, and this is typically compressible. So what we said last time is that these are typical problems. So for example, for Euler and Navier-Stokes, actually, in dimension 3, you know that there exists a solution which will blow up in finite time. This was this result of Siliris back in 1983 for Euler and Rosanova in 2008 for Navier-Stokes. So it's the typical type of model. You know that singularity can form. The question is how. Okay, so you ask the question, what do singularities look like? So let's start with the non-discrete problem. Let's just start with mu equals 0. So this is the ring of compressible Euler equation. Well, so in this case, the super baby model, the simplest thing that has been studied, in so many different ways since the 1920s, is the so-called Bargas equation. So it's typically non-viscous Bargas. It's typically something like this. We use just a function. And the reason why this thing has been so much studied is that this is one of these very few nonlinear models where you can compute everything. It's one of these nonlinear equations where you have a complete description. You can compute entirely the solution out of this thing, and what you learn is that the solution can form shock. Okay, so if you take a nice data, the origin, this is time 0, then in finite time, and you can compute everything, you can form a shock. And the typical way in which this kind of thing wants to form shock is the following thing. Your solution will remain bounded. What happens is that somewhere it wants to become very steep. Typically have something like this, okay? So it's typically, it's the derivative of u that becomes very, very large, okay? Something like a shock. And so this is so-called shock. Okay, so this is completely explicit. You can compute this. And you know that there is no issue of small data or large data here. You know that this thing can arise, even very small initial data can lead to this. It's some sense of in some sense, it's a different phenomenon. So more generally, this kind of equation here, in the case of Euler, it belongs to the class of quasi-linear wave equation. And this is, of course, an immense universe which has attracted considerable amount of works. And roughly speaking, what's behind the quasi-linear wave equation? When you think of a quasi-linear equation, is simply that I have a sound speed in my fluid. The sound speed depends on density, and density is evolving in time. Okay, so the way waves propagate in my fluid depends on actually what density is going to do. And what's something that people know has been have known for a very long time is that typically this kind of shock formation are expected in this kind of model, and it's really the world of small data work. There's even initial data that are very small. If you start cooking up some quasi-linear wave equation, it can lead to singularity formation, and there are very nice examples that were given by John essentially in the 70s, which was sort of pioneering on understanding this kind of issue. Of course, these equations are occurring, of course, it's occurring in fluid dynamics. Of course, general relativity is all about this equation, and Hermann observed this was an immense work in the 80s, before, that in fact, if you have special structure in your nonlinear problem, if you take a generic nonlinear wave equation, it will form small data blocks, this is what you expect. But if you have some specific structure in your nonlinearity, this is the so-called null structure, then actually maybe you can avoid singularity will not form, and we know that this had fantastic information, in particular for the study of Einstein's equations. So in the 90s, Alinak in some sense continued John's work and really ask, and really what Alinak was interesting is really understanding blow-up, understanding singularities, if you want, typically on models which violates Klein-Hermann's null condition, right? And sometimes you know that for specific, if you have some specific structure in your nonlinearity, shock will not form. But what about if it is not there? Can I sort of try to understand exactly the kind of singularity that can emerge from this product? And actually, Alinak was not only interested just in the first time of singularity, he was really trying to understand the complete
dimension 3.
So Alinak's work, it depends. Okay, so I'm not sure. What's the question? Yeah. So Alinak has,
that one is in dimension 3.
It's typically not dimensional. Exactly. So you have model in dimension 3. Maybe some have radial symmetry, etc. This is about producing examples of equations for which higher dimension, absolutely, for which you can actually understand some singularity formation. But what he really wanted
to work was in dimension 2.
I'm sorry?
Dimension 2.
But there are several papers, Igor. I think they are
early in dimension 2.
Okay, so I take your word for it, but it was not that dimension 1, right? It was already open. Okay.
It's just that Klein-Hermann showed in high dimensions you don't need the null condition for solutions of the nonlinear wave equation.
Say that again.
Klein-Hermann's thesis in high dimensions didn't require the null structure for global solutions in high dimensions. That's why I'm asking about them.
Because it's a universe. It's a question of decay and how you decay, etc. I'm giving a very rough picture.
Okay.
The only thing I want to say is the following thing. If you don't do anything, if you take generically a quasi-linear wave equation like this, you should expect that something like singularity formation can happen even from small data, unless you are in very high dimension or this kind of thing. But in this kind of picture, this is what you should think can happen to you. Okay, so and in some sense from there, I did not ask, what about, if I don't have this kind of structure, indeed, what kind of singularities can form and where can they go? Okay, and in fact, what he was interested, it's on quasi-linear wave equation, but it's a more general program which has also to do. So he asked for a quasi-linear wave equation, but this kind of question makes actually perfect sense for semi-linear wave equations as well. You can ask what singularities look like and how singularity can form. So actually, there's just something I would like to briefly explain. There is something specific. There is something very specific with wave equations, which I would like to explain, which is the following. Just to make my life easier, let's imagine that X is in R, and let's imagine that I take a very simple model. So I typically take, so this is the wave equation in dimension 1. So I take dtu minus dx squared u, and typically maybe I put some non-linearity u to the p. So this is very simple. So it means here it's not quasi-linear, it's semi-linear. The sound speed is 1. If you want, my light cone propagate at speed. Then the point I want to make is the following. So if this is x, if this is time, then I can do the following thing. What did we discuss so far? We discussed the following thing. So imagine that I give you my data at time minus 1. This is my initial data. It's a very nice initial data. Okay, then what we discussed so far is that there is a possibility that maybe at time 0, something like a singularity is going to form, and maybe in my problem, for some reason, I know that the singularity, so the first time, so my Cauchy data, if you want, breaks down. So the first time I blow up, say at t equals 1. Okay, and maybe my singularity, first moment when my singularity is 0 is exactly at x equals 0. But then if I have a hyperbolic problem, if I have a wave equation, typically a semi-linear wave equation like this, then as a matter of fact, I can look at a chunk of my data, of my solution. No? The point is that I explode it only here. Okay, so this is a very nice thing. And because this problem has finite speed of propagation, I can make sense of the evolution just generated by distance. If I have a heat equation or nonlinear Schrödinger equation, I cannot do this because I have infinite speed of propagation. I cannot define the flow, at least not just like this, beyond the first time of singularity. But if I have a hyperbolic problem, I can do that. Okay, now the question becomes, okay, but this is very interesting. So this is the first time of singularity, and this is exactly what Anna said, but then what we can do is that we can define a curve, which is the so-called blow-up curve, T of x, such that actually, for any point x below this curve, I'm very nice, and this is exactly where something nasty is going to happen. Actually. And Anna made a bunch of conjecture of what this curve should look like. There are very interesting works by Kafarid and Friedman on this question, and there is a series of work by Weyl and Zag. So we're talking, I think there may be something like 8 papers running from 2005 to 2015, which are all about, for any initial data, for this one-dimensional problem and for a certain range of exponent p, they describe completely what this curve is. And typically, the answer that we give you is the following thing, that what the curve looks like. It's something like this, and maybe it can form a cusp, then it's smooth, maybe it cups again, and so on and so forth. Again, the possibility that this cusp form is something that relies on the existence, the isolatedness, and the fact that these guys are in the picture. So the complete description, if you want, of the complete blow-up set has to do with the sharp description of the singularity on this curve. Okay, so the point I want to make here is the following thing. If you have a hyperbolic problem, so this is specific to the wave equation, you may not just consider the first time of singularity. There is another problem, which is in some sense about understanding the whole structure of the solution in space. Please?
I'm confused about the picture. This curve has slope less than 1.
Exactly. This curve here, it's always slope less than 1. And here, this is exactly plus 1. So this is plus 1 and minus 1, exactly plus 1 and minus 1. And this has to do with the plus 1 here. This is exactly the light curve that you can fit here below this picture. And the fact that this exists is highly non-trivial. Highly non-trivial. The fact that this is the picture. And this is not an example, this is a classification. Any solution will look like this. And the reason why it's a classification is because it's 20. Okay, they certainly know how to construct an example in higher T, but the reason why it's classification is really big because it's a one-dimensional proof. At some point in the proof, you have to say there is a unique solution to this elliptic equation, and this kind of answer, in 1D, sometimes you know, here you do. In general, it's probably just not true. probably much more complicated things that can happen. Okay, but the point I want to make is that these are two different problems. Understanding the first time of singularity, extending, understanding the whole phase space and the so-called maximal Cauchy development, if you want.
You have to have the right values, P though, right?
So for this picture and this to be true, you're absolutely right. You need P less than some value. Absolutely. There is numerology here again. And
so what is P star?
So P star in this case, so it's the conformal exponent. So it's the, I need to think of what my algebra is in 1D, but there is a number. So it's exactly the number below which, what you want to know is when is the conformal symmetry. So the conformal symmetry is a solution, is a symmetry of the free Weyl equation. You want to know when it's above or below the scaling for u to the p. So it gives you a number. Okay, so you need P star not to be too large. Okay, but this is not, it's just an example where we know how to do this. Well, the only point I want to make is that there are two very different questions here. One which makes sense just here, and this that you can propagate elsewhere.
If I make P equals 2,
you should be in business, yeah. You should be in the picture.
But P equals 3 won't do it, right?
No, P equals 3 will not do that. It's probably 3. I think it's 1 plus 2 already. Yeah, it's exactly. It's 1 plus 2 over this, so dimension 1. So this is exactly. This is P equal. Okay. So this is the. So this is the picture. So in the setting of compressible fluid dynamics, so if I go back to earlier, this is exactly the first result of complete description of similarity formation. If you want, in this sense, is exactly the work of Christodoulou. In 2006, where Christodoulou, so this is really for Euler, so this is dimension 3, this is compressible Euler, this is Euler in dimension 3. So Christodoulou is exactly doing this for you. So it's a construction. So it's telling you how to take an initial data at time -1, such that it will have a first time blow-up for which you will form a singularity, and it's giving you a complete description of what's happening beyond this. Okay, so it's really a complete description. It's a complete description of the shock formation in this. And you should think that
these are for special initial conditions, or
it's a construction. It's a set of initial data, and it's an open set. So it's
co-dimension.
No, so it's an open set. It's typically a stable picture. I'm sorry?
Within irritation.
Okay, so maybe there's some symmetry, and yeah, this is okay. So, but it's typically a construction. It's about choosing carefully the data so that you will have a first-time singularity, and then you will describe. You will have a description of this picture. Okay, and the important thing for what I want to say is that the basic one key thing in the proof is to understand what's happening at the first time of singularity. What's the typical picture that you have here? And the typical picture, so at the first time of singularity, so let's pretend that it's 0, what you see is a Bargas type blow-up on a scale. What you see here is that at the first, the way the first singularity forms is exactly, so you're in 3D, so something is happening, say, on R equal 1. So it's like some sort of derivative blow-up. So this is what's happening at the first time of blow-up. So this is a standard procedure in singularity formation. You lift what you know in dimension 1, you lift it to higher D using typically the fact that you're changing the geometry of the blow-up side. And then, so this is here. And then he understands the full picture, which of course is very nice, and which amounts, of course, propagating the information using the quasi-linear structure of the problem. So this is really what you see, the description, thanks to 1D Euler of the first singularity, and complete description then for Darwin. So this kind of pictures didn't also work at that particular area as well by Luke and Schmeck, related to questions as well. More recently, still on Euler, rather nice series of work. So
I'd just like to understand more precisely this as well. So it's here has to be rotational. What are it's an open set?
Yeah, so within some symmetry, it's typically an open set. It's a stable picture.
Tom, yeah, irrotation is open set within the class of irrotational.
It's all small irrotational data.
Yeah.
Full classification of what happens with the solution for all small irrotational data.
Okay.
I'm confused between the relation of Euler and Weyl. So Euler has finite probability velocity.
So earlier, this is just a simple picture in the sublinear case. So everybody light rays propagate at speed 1. And earlier it's more tricky because the sound speed depends on density, and density is changing. So indeed, the picture is more complicated indeed, and the answer for a certain class of initial data is exactly given to you by Viscosity.
Okay, but the velocity remains fine.
So it's typically the kind of singularity that happens is exactly this: velocity remains bounded, but derivatives become Euclidean. It's the typical picture of density and velocity remains bounded, but derivatives tend to become infinite. Okay. So this is the first picture, and as far as the description of the first time of singularity is concerned, there has been more recently this beautiful series of work by Buckmaster, Scholar, and Bacon. We tell you, well, so it's still for compressible Euler, 3D. And they tell you, well, there are other ways to form first singularities, and sometimes there are other ways if you want to lift the Bargas mechanism to a 3 dimension. So in particular, they show you how to construct shock with a blow-up point instead of a sphere, bigger point. Shock with R equals. Okay, so you don't blow up on a sphere at the first time of singularity. You don't blow up. You don't blow up at the point. But this is really they were interested in what's happening here at this very first time of the singularity. Okay, so really the picture is this one. So for Euler, you understand even in dimension bigger than 1, if you're on 2 and 3, you do understand some singularity formation mechanism. And because it's a hyperbolic problem, you can, as soon as you have a first time of singularity, you can carry out the program of understanding the full picture. And it's been carried out by Christodoulou in 2006 for a certain kind of initial data. So this is for the non-discussed problem. So now you ask, what happens if I add viscosity? Yes, so the question is, what happens if I add viscosity? So I put this so I really put Euler, if you want, on the right hand side, I have the viscosity. Then what happens is very clear. So this is typically, so this would become now the Navier-Stokes problem. So what happens is very clear. In dimension 1, there are no singularity formation. This is Meillet-Vasseur. This is Meillet-Vasseur. Something like 6, something like this. So immediately in dimension 1, dissipation is so strong that whatever you think could blow up, it will not blow up. No data will blow up. It's completely destroyed, and it's a standard thing. I mean, this is something that was observed, of course, in various different settings. In dimension 1, viscosity is a killer. It will completely destroy any sort of singularity formation. Dimension 2 is an open problem. It's not known. So there is a slight issue about what kind of initial data you consider. But let's say that if you stay away from vacuum, it's an endpoint problem. And in dimension 3, you know, again, this is the Rosanova result, you know, there is this finite type blow-up solution. So the question is, what are they going to look like? So, thank you. So the point I want to make is that if you try to fit this equation with the only blow-up mechanism that you know for Euler, that is essentially the examples given by Christodoulou or this example more recently given by Buckminster Scholar V. So you give them as data, if you want, for your Weyl equation, then there will be, this solution will not survive dissipation. Because essentially, the structure of the singularity formation that this solution have is that velocity and density remain bounded, but this is not strong enough a blow-up to survive Navier-Stokes. It's a theorem that if you want to see singularity formation for this thing, velocity and density must explode. Okay, so it means that you know that singularity formation can form, but the only examples you know in the non-viscous case are not candidate to form singularity. They cannot look like this. Okay, so it's a very simple thing. Something else has to show. Let me also stress that if you start looking at the parabolic problem, of course, this picture of hyperbolicity completely disappeared. Okay, so it's all about everything I want to talk about. It's just about this first time of blow. Okay, so this was really the question: what is the effect of viscosity, and can we construct? So there was no known example of blow-up solution for this problem. So this is something that's so this is something that we carried out. Maybe the theorem 2 if you want. So this is myself. And the theorem is exactly this one. So if you're in 3D, and if you choose, remember that pressure is equal to the gamma, so you need to choose gamma in a suitable way. So suitable choice of gamma, and I will be more specific next time. Then the picture that you have is that we can construct, so it's a construction. So there exists initial data, if you want, for velocity and density, which in many ways are very nice, such that you will form a singularity. And what's going to happen is that if you take the soup norm of velocity, it's going to blow up like 1 over t minus t to some power alpha. And if you take the soup norm of density, it's going to blow up 1 over t minus t to a power beta, and I in purpose took the same notation alpha beta are compact. It's a construction, it's an example of solutions to and this is for Navier-Stokes. This is with this viscosity, and this is free. So there are 3 things I would like to say about the theorem. So, the first thing I would like to say, so it's a construction. This is by no means a classification result. It's about understanding an example where you can understand the nature of the singularity. So the nature of the singularity, first of all, its implosion at the origin. Okay, it's a radially symmetric. The solution, if you want, as radial symmetry, blew up at the point is at the origin R equals. Second thing I would like to say is that we have a very clear answer to what is the influence of viscosity on this class and on this class only of singularity formation. The answer is very clear. Viscosity is lower order. Viscosity is lower order. In other words, the heart of the proof of this theorem is to construct new blow-up solutions to the compressible Euler, which are so violent that viscosity will not see them. Okay, so this is exactly what's going on here. In other words, the same result holds for Euler. Okay, we have exactly the same kind of a blow-up bubble for Euler, but it's a different regime from the one that were previously known. It's much more violent. Indeed, velocity and density explode, and it is so violent that, in fact, for these solutions, viscosity can be treated as a perturbation. This is exactly what we are going to do. And the first thing I would like to say is that because there is a deep connection, is, of course, defocusing index. And indeed, we propose a series of free preprints in which we present, if you want, a root map. Every problem has its, it's very different. NLS is a dispersive problem. Navier-Stokes is a parabolic problem. You have to be very careful. But the big picture and the global plan follow a similar route. This is how we present it. Okay, so what I want to do for the rest of these lectures is explain the root map, to root map of this construction. And I want to explain
what does quantized mean?
Quantized means that you cannot choose these guys. You cannot tell me, give me alpha, give me beta in an open range and cook up a solution like this. The way these numbers are chosen, you need to choose them very carefully.
And do you expect
something is discrete?
A general feature or something specific to your construction?
Well, I mean, you will see it very clearly. You will see very clearly where this conversation comes from next time. I promise that. Then you tell me if it's generic or not. Actually,
making sure we come the third time.
Well, and there will be a gamma function. This has been agreed. If you want, I can say this exactly like this. It's quantized because there is a gamma function, a nasty one in the function, and it tells us what we want to do. Okay, so I want to understand what is the root map. So the root map is this construction. And maybe I could tell you where we do this and it works, but I think it's more interesting to understand how this is deeply connected. This is really the continuation in some sense of works that started in the 80s. And until now, and this has been work that have been carried out actually by very various different group of people, and it's typically related to how do you describe singularity formation or singularity, because this is really what we first, this is this intuition that's going to tell us what we need to do. Another way of saying that is that there's really been, particularly at the beginning of the 80s, people really try to understand the singularity formation problem on baby models. Okay, so maybe the physics is gone, maybe what does it mean, what does it not mean? It was not the point. The point was to understand the mechanism, to understand the picture. And as a matter of fact, I want to explain to you what picture has emerged and how this picture actually gives you a hint of what you can do on this kind of problem, which of course are more complicated than the one that I'm talking about here, but they definitely give you a hint of where you should go. Okay, so let me start with sort of the simplest possible model you can think of, which is the semi-linear heat equation. And already there, you'll see that some things are completely understood, some things are completely open, and actually the picture is not that simple. So what is the semi-linear equation? So you do the simplest thing you can do. It's a scalar problem. So you just take the heat equation and you add a non-linearity, so typically u to the p equals 0. If you want to make your life even easier, you take u positive, so that you won't have any problem with that, but it's not necessary. So you should think that x is in RD, and I have this scaling exponent over 2 minus 2 over p minus 1, okay, which is going to appear in the picture. So here u is really scalar. And so because it's parabolic, because you have the maximal principle, there are millions of ways in which you can show that these things form a singularity. This is not about showing block, this is about understanding the singularity formation and how do you study this thing? How does singularity formation, how does it look? So the first thing you want to do remember, I told you there is something specific to these problems, which is that there is a scaling bias. There is a scaling bias. So what does it mean? It means that if you give me u of t and x a solution, then I can transform it into another one. I can look at 1 over lambda to the 2 over p minus 1, u of t over lambda square, x over lambda. For any lambda positive, this is again a solution. Okay, so the first thing you think of if you think of singularity formation is a solution which, for some reason, would want to form a singularity by concentrating in accordance with this scheme. Okay, so the simplest mechanism you can think of is the following thing. Imagine that your u will normalize a function lambda, and you have v of s. So actually, I'm going to call it time. D of time y. So what is tau? So tau is the rescale time. So d tau ds is 1 over lambda squared. And y is x over lambda. Okay, and so what it means, and you imagine that d wants to remain of size 1. Whatever. And imagine that lambda wants to go to 0. T goes to global, right? Imagine what does a function, you know, in some sense, this is compatible with the scaling of the equation. This is just saying that if I draw my u, so what I'm having in mind here is the following thing. It's the following thing. What I have in mind is the following thing. So this is x, this is u. And what I'm thinking is that my singularity will typically look like something that wants to concentrate here at the origin, right? This is the typical kind of mechanism that I'm thinking. And I'm thinking that there is a boundary layer here of size lambda of t, and maybe it's going to shrink. This is going to be bigger and bigger, and this is exactly what I'm doing here. I'm renormalizing, I'm zooming. Okay, so I'm zooming in space in y. So what I'm doing is I'm putting a zoom here, and I'm trying to understand what's going on. So instead of thinking of the singularity from the outside, I'm zooming inside, and I'm trying to understand what this function d is going to be. It's just a change of variable, but I go from a problem where t time is defined in finite interval and u becomes enormous, on a problem where I hope that, so tau, the new time, will be a global time, and the function v, what I want, so that's the key point. But in the first approximation, I would like to think that this function is going to be of size 1. Okay, if I can do that, this is exactly, so this is of size 1, this is going to 0, so this is including. So what I want is, I want to understand the renormalized. Okay, so this is a very simple thing. So instead, so you can trade the flow of u for the flow of v, and you can write down what the equation for v is. So it's a very simple thing. It will be exactly the same because it's the scaling of the equation. So you will have d tau v equals Laplace v minus v2 plus v to the b. Okay, it's the same equation because it's scaling. The only thing that changes is that I'm allowing for a dynamical rescaling. I'm allowing for this parameter to depend on time. Okay, so I will have a new term here. So which is probably going to be something like this. I have plus 1 over lambda ds and minus 1 plus y diagonal. Okay, so this is nothing. This is completely standard. This is, I'm just normalizing my flow, and I'm just trying to understand what the renormalized flow is going to be. Okay, so I hope it all becomes a question of understanding solution to this equation. Okay, and again, what I want solutions. I want, tau is going to be global. Okay. Renormalization, you will have a blow up in the end. What you want is that v to remain big. I don't want to see to be here. I could see maybe a solution that want to decay in some sense. But if I decay after renormalization, I'm not going to form a singularity. It's more or less automatic. What you want after renormalization, so you have a new PDE, you want to study it globally in time, and you want it to remain large. Okay, so it's always, you need your solution to remain big. Okay, fine. And you have an unknown in your problem, which is the so-called blow-up speed, which is this parameter lambda. So let me tell you what people did. This, which is actually basic. So the first thing people did, and we started with a gigacone in the 80s. But the first thing you say is, well, I don't understand this problem. I have no idea what's going on here. So let's try to do the simplest possible thing. What you want to choose. So how do you make large solution of a time-dependent PDE? Well, you look for time-independent solution. Right? So if you have a stationary solution, that's a very good candidate of this equation. But if you want to be stationary in time, this parameter here, the red one here, that it depends on time. So you want to take it constant. Okay, so what you can do is you choose. So this is the so-called scaling speed. So you choose lambda of t to be square root of t minus t, because it makes this parameter equal to 1. So if you do, so this is the so-called self-similar. So, okay, so you have the right to do that. So if you do that, you end up exactly with the following equation. D tau v equals Laplace d minus d to d, and you have the minus a half over t minus 1d. Why that? And to make yourself even easier, to make things completely trivial, let's say that V is radially symmetric. Okay, so let's think that Y, modulus of Y is R. Okay, I have radial symmetry, just to make things completely trivial. This is a simple, nothing can be simpler than this one. Okay, so this is your normalized equation, and now you ask yourself, what kind of solution to this thing do I have that are global in time, and for which I can understand what the solution looks like? Okay, so first, simplest thing you can do, you ask for stationary solution. Stationary solution. Okay, so you want to solve, so this is really now, this is really just an ODE, so you want to solve dr squared v plus d minus 1 over r dr v. So this is really your dr squared. So maybe let's stick with the Laplace. Just remember that the Laplace in radial symmetry is just a minute. So I want to solve this. Laplace v minus plus v to the p minus a half v. Let's try that. V is equal to z. Okay. So again, in general, it's a non-linear elliptic PDE. There are very few general answers. If you restrict to the radial set, it's much simpler. You can analyze it, but it still is not trivial. I mean, you have to think about it. So what gigacone should tell you is that when S is less than 1, so if you are in the energy subcritical case, there's only one solution. It's the constant solution. Where kappa is the constant. So there is a 2 over p minus 1. So where kappa is the solution to 1/2 2 over p minus 1 kappa. So it's a number. Okay, so what am I telling you? I'm telling you that in some regime of parameters, you normalize and you look at what a blow-up profile candidate could be. And what you see is you do this. You will normalize. So let's do it here. And you try to understand what the solution V of tau and Y wants to look like. Well, the candidate is that actually it wants to look like a constant. So that's something very funny. It means that when you zoom here, in this zone here, you see if you want your tip here is like it's like very flat. Okay, so it means that you want to look like a constant. So this is gigacone. What gigacone tell you, it's much better than that. They tell you that any blow-up solution under the energy space needs to have this as a blow profile. So not only is it a candidate, this is what happens. But of course, you understand, you cannot be a constant forever because you're in a function space where you're supposed to decay at infinity. Okay, so at some point, you need to forget that you are a constant. There is a reconnection problem. You need to reconnect to something else. Okay, but after renormalization, this zone in space, it's getting bigger and bigger. Okay, so it's a front. After renormalization, you zoom self-similarly, you look at what you have. What you have is something that wants to invade all space. It's a typical PHR front. It wants to invade all space, and there is a specific speed. You can compute this. And this was done first by two physicists from the Econormal, Drigmont-Kopianian, and then this was revisited by Hermann. This is all the 90s, so it's the speed of difference. So, from scratch, the first example on which you can put your hand on is not that trivial, actually, because, this thing is exactly telling you that once you renormalize, and when you look at this equation, the function space in which you want to work is very finite, because you need to accept typically these kind of solutions that are constant for a very long. Okay, but you can understand this. So this scenario is the scenario, it's a theorem, where SC is less than 1. So it corresponds to P not too large. As a matter of fact, so now you raise the value of P. Now you raise the value of P. What happened? Now you say, take larger value of P. So let's ignore SC equal 1. Let's take SC, and there is some number, SC twice. And actually, if I write down the self-similar equation, Laplace V, I'm sorry, minus a half 2 over P minus 1 P plus 5 not correct P. And if you raise the value of P, so again, when P is not too large, there's only one solution, the constant. It's a theorem, it's a Poiseuille identity. If I let the value of P arise, well, there are new solutions that arise. Actually, there are solutions, so typically I'm thinking of this as moody. So there are solutions that are profiles VRR that will typically look like rebels of energy and that decay at infinity. Yes, in fact, there are so-called self-similar solutions. In the simplest possible sense, it's typically this kind of solution, for example, that 20 years ago were ruled out by Spirac for the incompressible Navier-Stokes equation. It's exactly this kind of object that this is sort of the first thing you look for in this kind of problem. So in the case of the nonlinear heat equation, it exists in some regime of parameters. Okay? You can put your hand in this ODE, and of course the key point is that you have decay. This solution decay, and you can show that these are perfectly admissible blow-up profile. You will call this, if you blow up with this kind of blow-up, this is what people like to call type 1. You should think that type 1 in many ways, it's the simplest kind of singularity you can think of. You understand the point. What it means that you will normalize, you look for specific nonlinear objects, so you look for a solution to a nonlinear, it's not really elliptic because there's this funny operator here in the picture. You need to solve a nonlinear equation. In radial symmetry, you can do it. If you move away from radial symmetry, if you change the problem, it's very challenging. And sometimes you can show, like for incompressible Navier-Stokes, that these guys don't exist. Okay, so it depends. So this is type 1. There's something else. There's something else, and there's a long story, a very beautiful story actually, about this something else, and I cannot tell you the whole story. But this something else is everything else. What? You have this front singularity, and maybe it's very specific to the heat equation. We will go back to this question very soon. Then you have this self-similar solution. So what happens, and this is what you see in essentially all the remaining interesting problems, what happened actually, if you raise the value, And you discover that there are no, let me put it this way. If you raise the value, and actually you need to be, for the keep equation, you need to raise the dimension as well. You need to be in dimension bigger than 12. Then you have other scenario, which correspond to so-called type. What is a type 2? It's a very simple thing. I told you that what I want to solve this. I want to solve, so I'm going to have which is a p equals 0. So what did we do so far? We found global solution of this equation, which of course what we want is that we want them not to vanish. Okay, so they were of size 1, they were really of size 1. They remain of size 1 because they were given to me either by a constant and a perturbation of the constant, or by a stationary solution, which is of size 1. But something much more dramatic could happen. I could very well have solution to this equation that want to grow. Okay, they cannot grow up in finite time. It's forbidden by my renormalization. But I could very well, if I have something that wants to grow, it simply means that it's something that it's even more violent of self-similar blow-up. It's something even more drastic. Okay, so the question is, can you actually find solutions which have a much more violent behavior, which would correspond to completely different? What it means, you see. So actually, my equation is here. My equation is here. So can you find much more violent solution to this equation? And in fact, it amounts understanding, well, can you change? You made a choice. You decided that this parameter maybe was equal to 1/2 because this is the self-similar choice. But maybe there are more clever way of choosing this parameter to actually be able to compute completely different type of singularity formation. And this is exactly what you see in this picture. So you have so-called type 2 blow-up solution. And type 2 blow-up solution are something that are based on something very different. So one example, this is what should be said. So what governs, type 2 is not governed if you're on the blow-up profile. It's not given by a self-similar solution, that is a stationary equation to this. It's given by a stationary solution of the, it's given by a stationary solution. It's typically in this picture, it would be given by Laplace. You need to solve Laplace. So in other words, if I summarize it, you should think of it this way. When I have a self-similar solution to leading order, when I have type 2 to leading order, I look like a renormalized version of a function v, and to leading order, the function v looks like a soliton plus correction. But then this is possible only because the law for lambda of tau needs to be chosen in a very careful way. Alpha is compact. Okay, it means that type 2 is a universe. It's actually a huge universe. So interestingly enough, so it means that after renormalization, what you see is not a self-similar solution. What you see is something else. It's a solution to another elliptic equation. But then this is possible only if the blow-up speed, that is the quantity which you renormalize, if you want your boundary layer, satisfies very specific law, which you need to compute. So Professor Spencer asked me last time, are these numbers related to resonances? Right? So the answer here is definitely yes. And this is exactly what's going on here. These numbers are related to a spectral problem. Right? There is a lot that's hidden here. The spectral problems. And it's how do you compute type 2 blow-up solution is deeply related. The quantization effect is exactly related to this. At some point, you're computing the spectrum of a network. So the point of this type 2 blow-up is that there is a huge. The fact that you can have soliton blow-up, that is blow-up with soliton profile, solitonic blow-up, it's something that goes back actually to the 50s. This was discovered in nonlinear optics for the cubic nonlinear Schrödinger equation in 2D. This is one of these. This is almost the only example for which there is an explicit blow-up solution for which you can write. So it's a solution you can write exactly what these quantities are. You can compute Q. So we really had an example that come back from a very long time ago. In the setting of the nonlinear heat equation, it was discovered by Hermann Velasquez. And in fact, this kind of structure has been systematically studied. So there's been lots of absolutely fundamental work. And in fact, it is the picture for critical problems. And this I have no time to explain you this. So critical problems is typically, for example, when SC equal 1, this is exactly what people did. You know, if you think of this beautiful problem on wave map, Schrödinger map, in the year 2000, so there are various groups that worked on this problem, and this is exactly what's going on. What's going on, if you want, is that the simple picture of self-similar blow-up, that is, singularity formation is given after renormalization by a solution to this self-similar equation. This does not work for critical problems. You need something else. This something else corresponds to this kind of type 2 bubble, for which you need to learn how to control and how to compute the blow-up speed. And this kind of ideas really has been implemented in many various different settings. So in particular, for I should say for NLS, this beautiful work by Pierre Raphaël, Pierre Raphaël in 1999, and on geometric wave equation. This is exactly the work by Hermann. So this is around 2008. And this is exactly what these people understood is how do you create when you don't know what when the self-similar regime does not work for a class of critical problems, what becomes the relevant kind of bubble is this type 2 made case. So let's make two comments, and I will be done for today. The first comment is that these are only examples. You understand that we are even on these model problems, we are just at the very beginning of understanding what the picture, in particular after renormalization, can be. What starts arising, and there are, I'm thinking of beautiful results by Del Pino and his collaborator. What starts arising is the fact that it's not just about one bubble, it's about solitons interacting, solitons colliding, solitons being able to do very complicated things, or even non-radial structure that can start interacting. And we are just at the very beginning of seeing these structure arise. So this is really just the beginning of the discovery attached to this nonlinear structure. So this is the first thing. This is really just the beginning of the story. The second thing, and this will be what I will explain next time, is that now you try to apply this to typically defocusing NLS or compressible fluid, and you see immediately that none of this works. There's no chance to work. None of the objects that you know here that have been studied and that have given you very, huge knowledge of this phenomenon, these objects, they cannot be there because of the defocusing nature of the singularity, or because in compressible fluid, typically we get interested in radially symmetric solution. It's too simple in some sense. So these objects do not exist, but I will show you next time that there is a very simple way to, thanks to this intuition, to try and compute new type of solutions, which will give us answer.
Yes. So when you going back to the answer to the question from Akshay, although you promised the answer tomorrow. So when you're saying those exponents are quantized, those exponents are quantized for the example that you're giving, right? So you don't expect for.
So let me make myself crystal clear. For example, take these exponents here for the non-linear heat equation. Okay, so you take it radial symmetry, and you put yourself in the right range of exponents. Let's say if you put yourself in radial symmetry and you have a heat equation, you have a new tool you can play with, which is the maximal prime, which is describing, in fact, 90% of the proof that are devoted to the heat equation are maximal principle based proof. Okay? It's all about upper lower solution, Diaponov function, etc. So in this very case, it's a theorem that you have only two possibilities. You blow up infinite time, either your type 1, which has to fit with one of the two pictures that I give you, or your type 2, and people can compute this number for you. It's a discrete sequence, and I can tell you what this discrete sequence is. Okay, so in this picture here, quantization is really related to a spectral problem. You understand the spectral problem, you understand the picture. For the result that I mentioned for compressible fluid and defocusing, the way we have to choose this number is not related to a spectral problem. It's related to something else. So we need to choose them in a discrete way. It's very clear that if you try to continuously move this parameter, what we do will not work. It's very clear. But it's not the nature of the quantization. The reason why we have to adjust this parameter is not directly related to a spectral problem. I will show you this tomorrow.
Yeah. Okay. Maybe like what I meant is a little bit different. So like here, there's so your alpha is depending on P, I'm guessing, right?
Yeah. So
right. So in your
it's depending on K.
Yeah. So in your construction for the compressible oil, so you would expect that no matter what pressure law you take, right? So there's going to be an example.
Oh yeah. So
right.
It's a bit
So are your pressure exponents quantized too?
No. It's true to the gamma. So give me gamma.
Okay, given gamma, then you have the
okay, so now it's a little bit more tricky than that. I will, if I knew how to do all the gamma, I would. And actually, you cannot choose gamma. There are obstructions. You need to choose gamma in certain ranges because otherwise it's not true. You know, it's related to this question. Can you find dynamics? This is what I said. The question is the following. Can you find dynamics for Euler such that dissipation is lower order? The question is, it depends. The answer is, it depends. In particular, there are ranges of gamma for which the kind of objects that we want does not exist. So it depends. There is no obvious answer to this question. Are there blow-up dynamics for Euler such that dissipation is lower order? It depends on the range of the nonlinearity. It depends on gamma. So clear.
Gamma is not quantized.
Gamma is not quantized. Gamma is given to you.
It depends on the range, but it is a range.
Yeah. That's what I mean, that is what I was meaning. I mean, that guy is not going to be discrete. Right? So you're expecting there's. Then of course I can understand that if the magnitude is a certain thing, then the viscosity is going to win. Yeah. That's what I mean.
Gamma is an open range, but the speed.
Yeah, but then the speed, of course, is depending on the gamma. Yeah, that I find more natural somehow. I was kind of surprised that that there's going to be like a discrete set of powers.
It's a little bit more mathematical. The example Krieger-Schlag-Tata, they come up with a term where actually this is it's not quantized. So now there is an issue of function space. So things be it's a question of now there is an issue of regularity. But you know what's the link? It's not completely clear.
No, fair enough. I mean, that is what I wanted to understand.
Gamma is-
To have
gamma
a range of powers.
No,
for
absolutely,
networks.
absolutely.
That's
Absolutely.
other questions?
Is that range of gamma alpha and beta independent of gamma?
So I will show you these guys tomorrow. Okay, so.
Yeah, there's a question over there.
So for Weyl, there are two types of singularity. There are this shock, and there is this compression singularity where the density blow up. Does these two phenomena how do they fit in this type 1, type 2 dichotomy?
So this you will know tomorrow. What I will show you.
He's trying to indicate we need more time to work. Will be.
But see, the only point I want to make is that this is a picture that's been developed over 40 years now. And it doesn't give you the answer, but it's the way you have to go through it. You have to walk the way to find another way and just add the next stone on the route in some sense. What we do is not orthogonal at all to what's being done here. It's the other way around. It's in the continuation.
That does not seem to be. Other questions? Thanks.